Now, if the variables are really independent, the expected frequencies and the observed frequencies would be the same, or close enough in the sample data. So it's just like in the last section. So when we did a hypothesis test about mu, and if mu was claimed to be 5, we didn't really expect to see an X bar of exactly 5, but if it were close enough, we would end up failing to reject HO. It would only be when we got an X bar value way far away from the claim that would make our p-value really tiny that we would reject the claim about mu. So the test statistic here will involve looking at the difference between the expected frequency and the observed frequency for each cell. And then we want to find some way to find kind of this total difference of all of those differences. And then the larger the total, the smaller the chances that you could find that test statistic given the assumption of independence is true, which means in that case the assumption of independence is probably not true, and so we would reject HO. So how do we find this new test statistic? Well, first we're going to find the difference between the observed and expected frequencies for each cell. Now, some of these differences will be positive, and some will be negative. We've seen this happen many times now with when we did standard deviations and variances back in the first unit, and in the last section when we were looking at residuals. And so in this case, so that when we add those we don't just get 0, we're going to square each of those differences. But now, before we add those, these squares could be large just because the frequencies are large. So some cells we expect to see more things than others, so it doesn't make sense to just add up all those squared differences and treat them all with an equal weight. Okay, so the next step we need to do is we need to divide by the expected frequency of each cell to kind of scale them, to kind of normalize them. Then finally add up all of these fractional values. Okay, and this gives us a new test statistic called chi-square. So the symbol for chi-square is kind of, this looks kind of weird, looks just like it is kind of just a fancy X, the square symbol next to it. And in here we're going to, this O stands for observed frequency, and the E stands for the expected frequency. So the observed frequencies are given, the expected frequencies are computed, assuming independence. So what we would expect in each cell if these two variables really are independent. Alright, well, this new test statistic, so up until this point the two test statistics we've had have been the Z statistic from the normal distribution and the T statistic from the T distribution. Okay, this new test statistic is going to have a different shape distribution because in the numerator here we're taking differences and squaring them, which is going to be some non-negative number, and then we're dividing it by an expected frequency, which is again going to be a non-negative number. So this quantity can never be negative. So we're not going to have some distribution whose axis goes from negative infinity to infinity like we did with t-scores and z-scores. So what does this distribution of chi-square look like? So the random variable chi-square has different curves depending on the number of rows and column categories in the contingency table. It's skewed to the right, okay, so it's not symmetric like the other distributions we've looked at, when the number of categories is small, and it gets more symmetric as the number of categories increases. Now, since the test statistic involves squaring the differences, the test statistic is always greater than or equal to 0. So in this case, our distribution curve starts at 0, so these values of chi-square, and they extend out here to infinity. Okay, so we don't have this symmetric distribution with 0 in the middle like we did with t-scores and z-scores. Okay. And this df here, we don't really need to worry too much about since we aren't using tables anymore, but this stands for degrees of freedom. But again, this number depends on the number of row and column categories. So as was stated in the paragraph above, as that number of row and column categories gets larger, we see this really right skew distribution, but as this degrees of freedom number, again, depends on number of rows and columns, categories, as that number gets higher, we see that this distribution gets more symmetric looking. Now, even when it's symmetric, it's not going to be symmetric about 0, like our t and z scores. It would be symmetric about, some positive value over here on the axis. All right, so this new distribution is what we call the chi-square. This new distribution is what will be used in this chi-square independence test in this section. So just as with previous hypothesis tests, all the steps are the same, except for the assumptions and the test statistics. So each one we have different assumptions we're going to be testing, and there's going to be a new test statistic, but all the logic after that is still the same. In this case, there will not be a parameter, so we're going to have phantoms, but without the p, so one letter short.